Hi everybody, my name is Alim, and today I'll be talking about Catena, which is an efficient to verify non-equivocation scheme built on top of Bitcoin. And Catena is actually a very simple idea, but it has surprisingly powerful applications like public key directories. So let me start by explaining the title. So what is this non-equivocation thing? And to explain this, I'll use a public key directory as an example. And this directory, every time period I, would publish a digest SI of the directory. And that digest is simply a Merkle tree hash. So what non-equivocation says is that at every time period I, the server only publishes a single unique digest SI. So for instance, at time 1, Bob and Alice see the same directory S1. And when the directory is updated at time 2, Alice and Bob and others will see the same history of digests S1 and S2. So this is good because Alice and Bob can monitor their own public keys and detect impersonation. So in this case, Alice checks, she's okay. Bob checks, he's okay. And what this means is that if the server wants to impersonate Alice or Bob, it has to do so in plain sight. So for instance, here, the server inserted a fake key for Alice to trick Bob into using it. But because of non-equivocation, Alice and Bob see the same directory, and Alice can detect this fake key. This is not to say that their secrecy is preserved, because Bob could use that key anyway before Alice has a chance to detect it and yell to the world that she's been impersonated. But this is to say that such attacks don't go undetected, which is a step forward. So to summarize, non-equivocation just simply means saying the same thing to all of the people. Even if the thing you're saying is incorrect at the application layer, like this statement 2 here where Alice was impersonated, at least we can detect such incorrect statements. Now what is equivocation? Well, at time 2, the malicious server could simply publish two digests, S2 and S2 prime. So in S2, Alice's key is left intact, but Bob is impersonated. In S2 prime, Bob's key is left intact, but Alice is impersonated. So when Alice checks in her view, everything seems fine. Her key is the same. However, Bob is impersonated there, and Alice will use a fake key for Bob. When Bob checks in his view, everything seems fine, but Alice is impersonated, and Bob will use a fake key for Alice. So as a result, the man-in-the-middle attack is possible, and this is kind of undetectable. Alice and Bob don't have a way to check that they are seeing the same directory. For that, they would need a secure channel, but that's what they're using the public key directory for in the first place, to establish that secure channel. So this is kind of a bummer. If you say different things to different people in a public key directory, you can equivocate and you can man-in-the-middle your users. So we'd like to solve this. And this comes up a lot in public key distributions for HTTPS, secure messaging, and pretty much any work that says we assume a PKI. And it also comes up in Tor directory servers, which can equivocate to victims about the set of onion relays and de-anonymize them. And it comes up in software transparency schemes where a software vendor like Bitcoin itself would like to make sure no malicious binaries in its name have been published. Just like in public key distribution, Bitcoin needs to see the same transparency log as all of the people downloading Bitcoin. So what are our contributions? So we built this Bitcoin-based append-only log that is as hard to fork as the Bitcoin blockchain. But importantly, it's efficiently verifiable. You don't have to download full blocks to verify our log. In particular, you only need to download 600 bytes per statement. A statement is something like a Merkle tree hash, a public key directory digest. And you only need to download 80 bytes per Bitcoin block. You don't need to download the whole block. And we implemented this in Java, and our code is open source. So the outline for the talk will be first, let's go over Bitcoin and explain how Bitcoin transactions work and how Bitcoin prevents double spends. This is super important to actually understand how Catena works. Then I'll go over previous work. Then I'll go over our design and how to scale it. Okay, so this thing comes up a lot these days. What is this blockchain? It's just a hash chain of blocks. Block n contains a hash of block n minus 1. So each block has a hash pointer to the previous block, and the arrows indicate hash pointers here. Each block has a Merkle tree of transactions. And everybody agrees on this hash chain of blocks via proof of work consensus, which I won't talk about too much, but we do assume that it works. So attacks like the one Maria described are problematic, and we do need to fix those in order for our assumptions to be reasonable. So let's talk about Bitcoin transactions. They have two purposes. The first purpose is to just mint coins. So here transaction A says, hey, look, public key Alice with public key Alice minted for Bitcoins. And says that is it has this thing called a transaction output, that little circle over there, and the output just specifies the number of coins and who owns them. And the second purpose is to transfer these coins. So Alice might want to give 3 coins to Bob and leave a fee to the Bitcoin miners who manage this blockchain. And for that, Alice would create this transaction B with another output that says BKB has 3 Bitcoins. So now the question is, how do we link this transaction to the previous one? We do that via something called a transaction input. The transaction input has a hash pointer to the output being spent. So here transaction A is being referred to by the input in transaction B. And more importantly, transaction B's input has a signature that authorizes the transfer of coins from TXA's output to TXB's output. So furthermore, what you can do in Bitcoin is you can embed data in transactions. So we actually leverage this to build a log. Alice can put up to 80 bytes in that transaction TXB. So to summarize here, Alice gave Bob 3 Bitcoins. Bitcoin miners collected 1 Bitcoin as a fee. Outputs specify coins and who owns those coins as a public key. Inputs have hash pointers to outputs being spent and specify a signature under that output's public key. And this can keep going. Bob can give Carol his Bitcoins. He can transfer 2 Bitcoins to Carol, pay 1 Bitcoin to the Bitcoin miners, and so on and so forth. And importantly, what Bitcoin actually guarantees is there cannot be double spends. So here, for example, the way Bitcoin does that is by maintaining this very simple invariant. It just says that a transaction output can only be referred to by a single transaction input. So this picture right here simply cannot happen in Bitcoin. You cannot have 2 different transactions that have inputs pointing to the same output. Bitcoin doesn't allow you to do that. Bitcoin miners prevent that from happening. So the moral of the story here, why did I tell you all of this? The reason I told you all of this is because I want you guys to look at this picture and understand that either TX2 can be in the blockchain or TX2 prime, but not both. So when I first realized this, I thought this was really cool because if we can put statements in these transactions, we can also implicitly prevent equivocation. So now we can either have S2 or S2 prime, but not both. So this is the key idea behind Catena, and it's actually a very simple realization. Okay, let's go over previous work now. So the way previous work builds a log on top of Bitcoin is by just embedding statements in transactions, but they're kind of unrestricted about how these transactions relate to one another. So as a result, if I want to be certain that there's no S3 prime in the blockchain, I can't do any better than downloading full blocks to be sure that I haven't missed that S3 prime. I could ask a Bitcoin peer-to-peer node to filter the block for me, but that node might lie. Or I would be vulnerable to Sybil attacks on the Bitcoin peer-to-peer network. Where a bunch of malicious nodes are created that just lie to me. So this is not very good for efficiency. So our work simply requires that a new transaction spends the previous one. So this implicitly tells us that there cannot be an inconsistent statement because it would require a double spend. So basically the difference is quite simple. It's just this. If I had one slide for the presentation, this would be it. Okay, so let's talk about the design in more detail. We have this thing called a lock server. So this can be the public key directory that I talked about before. And it starts with some Bitcoins. And to start a log, it issues something called the genesis transaction of the log. This is the first transaction in the log, and it's basically the log's public key. And the way it does this is by just sending coins from itself back to itself and paying a fee in the process. And now to issue the first statement in the log, it creates TX1. TX1 has an input that spends GTX's output. Coins are again being sent from the server back to the server. And because TX1 spends GTX, there cannot be an inconsistent TX1 prime that commits a statement S1 prime, because that would require a double spend. And so on and so forth. If you want to issue the next statement, you create a TX2 that spends TX1. Coins are being sent again from server back to server. Inconsistent statements cannot happen without a double spend. So what this means is that if the server is compromised, it still cannot equivocate. So in particular here, if the server wants to issue 2 statements S3 and S3 prime, it has to double spend the output in TX2, which Bitcoin miners prevent. So this is nice because it's as hard to fork as the Bitcoin blockchain, because to double spend in Bitcoin, the best you can hope to do is fork the blockchain. But it's efficient to verify, and I'll talk about that in a second. The disadvantages, however, are that before we can accept S2, for example, we need to wait for 6 more blocks to be built on top of block N. And this is just a heuristic. In practice, you might actually want to do more. So that amounts to around an hour delay before you can accept a statement. And the other thing is that you can only issue a statement every 10 minutes. This is because it doesn't make sense to issue 2 statements in a block. You might as well just merge them into a single statement. And Bitcoin blocks are published every 10 minutes. And we have to pay Bitcoin transaction fees to do this. And when we wrote the paper, the fees were low. I think they were around 12 cents. I think now, however, they're more like 70 cents. Bitcoin went up. So let's talk about how clients verify this log. So suppose I have a mobile phone that is, let's say, a messaging app like WhatsApp, and I have this log server that is WhatsApp's public key directory server. And I have the Bitcoin peer-to-peer network, which stores the blockchain, and it has around 7,000 nodes. In order to audit the log, I need to have the log's Genesis transaction. So this is important to understand. This is the public key of the log. I can only prevent equivocation with respect to a log, and I need to identify a log with a Genesis transaction. So once I have that, I need to get it from a trusted source. I am sure that all the statements I get are a linear history of statements. So the way I do that is I ask the Bitcoin peer-to-peer network, hey, what are the next block headers? I get back the headers. They're 80 bytes each. I verify the proof of work. Then I ask the log server, hey, what's the first statement in the log? This guy tells me, hey, look, it's TX1. It has this statement 1 in it. Here's a Merkle proof. And this whole thing is just 600 bytes. I check that TX1 spends GTX. I check that TX1 is in the Bitcoin blockchain by verifying the Merkle proof. And I keep doing this. I ask for new block headers. I ask for the next statement. I verify that the transaction spends the previous one. I verify that the transaction is part of the Bitcoin blockchain. And as a result, I get non-equivocation if I wait for sufficient Bitcoin blocks on top of block N here, for example. So this is great because we only need to download very little data. In particular, with the current size of the Bitcoin blockchain, if we had 10,000 statements in a log, we would only need to download 41 megabytes. Which is an improvement over previous work, which kind of requires you to download full blocks to be really certain you're not being equivocated to. Okay, so let's talk about scalability. So this is kind of a problem because the Bitcoin peer-to-peer network only has 7,000 full nodes, and each node has around 117 connections, I believe, and that amounts to around 819,000 incoming connections that this network supports. So if we had a bunch of Catena clients for a public key directory for a popular app like WhatsApp, and each client opens up around 8 connections to this network, we kind of unintentionally DDoS Bitcoin, and obviously we don't want to do that. So to fix this problem, we introduced this thing called the header relay network, and this is just a way to scale up the Bitcoin peer-to-peer network's capacity for incoming connections. And this header relay network just downloads the block headers from the Bitcoin peer-to-peer network and allows Catena clients to fetch those block headers. So now the Catena clients can connect to this network and request block headers. And we can implement this in a bunch of ways with volunteer nodes, with existing blockchain explorers like blockchain.info, with Facebook feeds, Twitter feeds, GitHub feeds, and so on and so forth. There's actually one implementation in Ethereum that serves Bitcoin headers via the Ethereum blockchain. And there's a bunch of ways of building this. And importantly, if someone hacks this header relay network, it doesn't by itself allow him to equivocate. The attacker still needs to take advantage of an accidental fork in Bitcoin, or the attacker still needs to adversarially mine. However, if the attacker does have control of this network, adversarial mining attacks can be somewhat easier. But the same thing is true for an attacker who would control the Bitcoin peer-to-peer network. So in that sense, we hope that we haven't introduced too much, a bigger assumption than the Bitcoin peer-to-peer network. This is really just an extension of it. Yeah, so to conclude, what we did here is we enabled applications to efficiently leverage Bitcoin's publicly verifiable consensus. So clients only need to download transactions selectively rather than the full blockchain. This amounts to downloading 41 megabytes for a small log rather than gigabytes. And why I think this matters is because we can hopefully build better public key directories with this. We can maybe secure things like certificate transparency against equivocation. We can build Tor consensus transparency on top of this. We can definitely build software transparency schemes very easily with a Catena log. And in general, we can take any fork consistent system and give it full consistency. So things like Sunder, Spork, for integrity, so on and so forth. And yeah, for more, please read our paper. And I'll leave you with this picture of previous work in our system, and our code is at that address.
Hi, Cristina Anita Rotaro, Northeastern University. So it seems that what you really need is this abstraction of like digital currencies and the double spending. Bitcoin is one of the many.
Yeah.
Did you think about, I mean, you're coming from MIT, Ethereum, and there's several other zero cash. And so did you look at other Bitcoin-like systems and what is exactly what you need from them and how generalizable is what you propose? Because, for example, there are attacks against Bitcoin double spending and why majority is not enough and things like that.
Right, yeah. So I did look at Ethereum. I think the reason I didn't use Ethereum is because it has these other problems with its proof of work consensus that people wrote papers on. The other reason is that Ethereum block headers are too large, actually, much larger than Bitcoin block headers. This is not in the paper, I just realized that after, actually. And another reason was, at the time when we wrote the paper, we wanted to implement this, and there was no way to do light verification in Ethereum. This changed by the time our paper got accepted. So I could see this being also done in Ethereum, and it would be interesting to see what the bandwidth would be, because Ethereum block headers are bigger and there's more of them, and it uses a different consensus algorithm.
Hi, Eleftherios Kokoris, EPFL. So I'm going to stick into your sale pitch of it's as hard to fork as Bitcoin. The thing is that it's not extremely hard to fork Bitcoin. We just don't do it because you are going to double spend 5 Bitcoins, it's not that much money.
Right.
But once you move to that, double spending is actually attacking end-to-end encryption. Aren't you worried that this makes Bitcoin more vulnerable to such attacks by using it? And in the process, it will actually break Bitcoin because three-letter agencies would try to double spend.
Right. Yeah, so that's a very good point. How hard is it to fork Bitcoin, and will it get harder if we build other things on top of it, like this or like colored coins? And people have looked at this, and I don't have any answers to that question. I really don't know. I hope that Bitcoin becomes useful enough and people want to further secure it, and it'll be hard to fork. So far, we've had accidental forks. I hope it withstands attacks. That's all I can say.
I think there was a paper in CCS from Arthur Gervais showing like how hard it is to fork Bitcoin, and it's like you can double spend if it's worth like a few dozen $K.
Right. Yes.
It's
yes.
not that much
Yeah.
for NSA to start breaking end-to-end encryption, right?
Right. It could be. Yeah, that could be true. Yeah.
So at the moment, you listed a few of the applications of this, which make sense when it costs 12 or 70 cents. Are there more applications you have in mind that you could use if it only cost 1 cent or a microcent to do a non-equivocation? Log append?
You know, I didn't really think about that too much. I was so excited about public key distribution that I was like, wow, this is really cool. Well, everybody's just doing it slightly inefficiently, and you can do it efficiently. I think public key distribution is the killer app. Not sure. I'll get back to you on that.
Okay, great. All right, let's thank Aline.